Okay, so we are getting started with something called uniform accelerated motion. Now, motion and movement is basically what we do every day. Otherwise, life as we know it, without being able to move or being in motion, was going to be a problem. And there are many things which move us, human beings, animals, and also other non living things, they move. For example, cars. So it's actually very, very important that we are able to study, we are able to analyze, and also we're able to predict how things move around us. Without being able to predict how a bicycle which is near you or how a car which is near you is going to move, that could be very dangerous because you could be involved in a car accident because one, maybe you misjudged how fast the car was moving just by looking, or you thought you had enough time or something like that. So it's very, very important. It's actually a matter of life and death for you to be able to predict how things are going to move. Okay. So the kind of motion we are interested in is something called uniformly accelerated motion. There are a number of ways. There are certain terms which we use to describe motion. For example, distance. Distance is the length which has been moved by a particular object, and distance in a specific direction is something called displacement. So if you move a particular distance in a specific direction, that's called displacement. How fast you're covering the distance, that is what is called speed. How fast you're covering distance in a specific direction, that is what is called displacement. So we're going to look at these terms on how we describe motion. One of the things which we are interested in when you are describing motion is whether the speed, which we are going to see what it is, or the velocity of an object is changing. If the speed of an object is not changing, things are very easy to predict, but generally, such a case where something moves without the speed changing does not quite happen very much. It happens sometimes. You can force your car to move or at a constant speed, but somewhere along the way you will have to change the speed, either because you're trying to overtake some other car, or maybe there's an accident in front of you, or some people are trying to cross the road, so you have to reduce your speed. So usually most of the time what happens is that as you are moving or as you are driving, whether you're running or you're walking, you will need to change your speed at one point or another. When you change your speed, whether you are changing your speed for the purpose of moving faster, or you're changing your speed because you want to slow down so that you don't bump into someone or you don't collide with the car in front of you, that is what we call acceleration. Okay? When the velocity or when the speed of an object which is in motion changes, that is what we call acceleration. So our interest is in something called accelerated motion. Motion in which the velocity or the speed of the object in motion actually changes. We are also actually particularly more interested in something called uniform accelerated motion. Now, the uniform in this case means the same. So during the motion we are interested in, we make the assumption that the acceleration, which is how fast the speed or the velocity of an object is changing, is going to be the same. That is the assumption you are making. The acceleration or the velocity, how fast the object in motion is changing, is going to be the same. Hence, the topic uniform accelerated motion. This is a very, very restricted case. However, this same case of uniform accelerated motion allows us to actually study, it allows us to analyze, and also predict things fairly accurately. In reality, When you are moving from point A to point B, or you're driving a car from this point to that point, yes, there is going to be acceleration because your velocity is going to change. However, that acceleration which you're going to experience as your velocity changes when you are actually doing things in reality is not going to be uniform. It's not going to be the same. So most of the motion we experience in day-to-day life is something called non-uniform accelerated motion. That is the most general case of motion which happens. And it's a bit difficult to predict. If things are moving in a non-uniform way, then the predictions become very, very difficult. So in this case, in this course, we restrict ourselves to the case where the acceleration has got the same value, and that makes it possible for us to predict where an object is going to be after a certain amount of time, how much distance the object has covered after a certain amount of time, and stuff like that. So, like I've said, our interest is in uniform accelerated motion. Now, this uniform accelerated motion, we're going to look at it from two different points of view. We are going to use graphs to see how the motion of an object can be presented on a graph, and more interestingly, how the velocity of that particular object changes using graphs. The other thing we're going to use after we look at how to present motion of an object on a graph is we're going to use mathematic-like expressions which are called equations of motion. Some of you who did physics in grade 10 or grade 11, you could have come across some of these equations of motion. So we are going to show you how you come up with these equations of motion, where they come from. It is not necessary for you to understand, for you to memorize how to come up with these equations of motions. What we want to do is we want to show you how you come up with these equations of motion so that your understanding can increase. Okay. So, the study of motion, or the study of how things move without looking at what's causing the object to move. Maybe you are running because you saw a snake, or maybe you are running because people are chasing you. So if we just look at how you are running without looking at why it is you're running, then that is what is called kinematics. When you look at what's causing you to run the way you're running, then that is called dynamics. Okay. So during the course of this lecture, we hope and expect you that by the time we are done, you should be able to define or describe motion in terms of distance. So you should be able to define distance. When someone asks you what distance is, you should be able to define what distance is. Something called displacement. Now, distance, for a start, is the length moved by an object. Whether that length is in a straight line or that length is in a circle, in a curve, it doesn't matter. Distance is the length moved by an object. That's what distance is. Then you should also be able to describe motion in terms of displacement. Displacement, on the other hand, displacement, yes, is a kind of distance, but displacement is different from distance, because displacement is the straight line distance between 2 points. Okay, it's a straight line distance between 2 points. That's what displacement is. Then speed is basically how fast you're covering the distance. So we look at how much distance you've covered. Then that distance you've covered, we divide it by the time you have taken to cover the distance. So basically that's the simplest explanation of what speed is. Velocity is also relates to how fast you're covering displacement. So we look at how much the displacement is, how much displacement you've covered, then we divide the displacement by the time it has taken. Then the other thing is acceleration. Acceleration is just basically how fast, or how fast is the speed, or how fast is the velocity changing. That's what acceleration is. So we expect you to be able to describe motion, accelerated motion, in terms of these ways, in terms of this language of distance, displacement, speed, velocity, and acceleration. So we're going to see that. The other thing we expect you to do is when we give you a graph, you should be able to interpret what's happening. Sometimes you can give in terms of distance, how much distance has been moved, what's the displacement, what's happening with the speed, velocity, and also the acceleration. One of the most important graphs which we are going to show you, and which is very important to our study of what we are trying to do, is something called a velocity time graph. Now, this velocity time graph shows you how the velocity or the speed changes with time. That's what it does. So after each and every second, we show you what the velocity of a particular object is. Okay. With this velocity time graph, the reason why we are interested in this velocity time graph is because it's a graph. The area under the velocity time graph, if you work out the area under the velocity time graph, that area is equal to the displacement, or it's equal to the distance which has been moved by a particular object in that particular time when the graph was like that. The other thing about a velocity time graph is the slope or the gradient of the velocity time graph. The gradient of the velocity time graph is very important to us because it happens to be equal to the acceleration. So if when we give you a velocity time graph, then we ask you to find out how fast is the speed or the velocity changing. Then you have to work out the slope at that particular region. When you work out the slope at that particular region, that slope is going to be equal to the acceleration. On the other hand, when we ask you how much distance or displacement has been covered, then you have to work out the area under the particular time or interval in question. So basically that's what we are up against. Okay, so let's start with displacement and distance. These are the terms which we use to describe motion. So in the case of distance, like I've said, this distance and displacement are related. Distance refers to the length that has been moved by an object. This length you can move in a straight line, so you cover this length, or you can move in a circle, or you can move in a zigzag. As long as we measure this length, that is what is referred to as distance. And the symbol for distance we're going to be using is d. That's d. Distance has got a size, which is how much length you have moved. However, distance does not say anything about the direction in which you are moving. So distance in itself, by definition, lacks information about the direction in which you are moving, as much as we can tell how much distance it is, but there is no information about the direction in which you're moving. So distance is an example of a scalar quantity. Displacement, on the other hand, is the straight line distance. If you've got point A and point B, then you draw a straight line between point A and point B. Okay, so displacement is a straight line distance. Why do we mention distance again? Because this straight line length, you have to move this length. So you are going to move in a straight line. Okay, so when you're talking about displacement, we are basically saying you move in a straight line. So the straight line distance covered by an object. And apart from that, on that straight line requirement, there is also information about the direction in which you're moving. So you also need to tell us the direction in which you're moving. Are you moving 100 meters west, or 100 meters east, or 100 meters south? So that is a distinction between distance and displacement. Distance refers to the length an object has moved. This length can be a straight line, or this length can be a circle. You can move in a circular path, or you can move in a zigzag path, as long as you have covered a particular length. And it does not have any information about the direction in which you're moving. Displacement, on the other hand, is a very specific thing. It is a straight line distance. So you have to move in a straight line. Then, when you move in a straight line, you're going to cover some particular distance. The other thing is the direction. You need to tell us the direction in which you're moving. So, in the case of, like we have here, in the case of distance, you just say 120 meters. In the case of displacement, you tell us 120 meters west. So displacement is a vector while distance is a scalar. Is that clear? Between distance and displacement?
Yes.
Okay. The next bit is something called speed and velocity. Speed and velocity are also related, just like distance and displacement. The relationship here is that both speed and velocity measure how fast you cover distance or how fast you cover the displacement. So the how fast you cover the distance, that is what is called speed. The how fast you cover the displacement, that is what is called velocity. So for you to find speed, you could divide your distance by the time, or you could divide the displacement by the time. The distinction really is, yes, you can do that. However, there are two types of speeds or velocities which we're interested in. One is called something called instantaneous speed or velocity. The other one is something called average speed or velocity. Now, instantaneous speed or velocity is basically what is the speed or velocity of an object at a specific point in time. When we are talking about instantaneous speed, we are asking about what is the speed or the velocity of an object in motion at a specific point in time. This instantaneous speed or velocity is what the police are interested in when they mount a speed trap. When the police mount a speed trap, they are interested in your speed or velocity where the speed trap is, and at that particular point in time when the speed trap is present right there and then. Okay? If there is no speed trap, then the police are not interested. Okay, so at that particular point, it doesn't matter whether in the morning when you pass through that point, you're driving below the speed limit. But at that particular point, when the police are there, then they have mounted a speed trap. They are interested in your speed or velocity. Basically, they are interested in how fast you are covering distance or displacement. That is what is called instantaneous speed or velocity. Okay. Are we clear about the definition of instantaneous speed or velocity?
Yes, sir.
Yes. In physics, now, with instantaneous speed or velocity, which is the velocity or the speed of an object in motion at a specific point in time, you will agree with me that objects usually tend to have different velocities at each point in time. So if you just start measuring what the velocity of objects are at each point in time, what you're going to end up having is you're going to end up having a lot of values of this instantaneous speed, which is a lot of work and it is cumbersome. So in physics, what we do instead, we try not to keep a lot of values. However, that does not mean that we are not interested in the instantaneous speed or instantaneous velocity, because in our definition of time, okay, our definition of time which we use in physics is different from the definition of time which the police use. The police are interested in what was your speed at 10 hours when they mounted the traffic light, the speed trap, okay, or what was your speed at 10:30, or what was the speed at 10:15. That is the definition of time which the police are interested in, and they're interested in your speed at that particular time. Our definition of time in physics is a bit different, because in physics we measure time, or we define time. If you remember from what we started, our definition of time is the duration during which a process or an event occurred or continues to occur. So, in our definition of physics, we are interested in how long something is happening, for how long. So if it's happening it happens for 10 seconds, that's what we're interested in. 10 seconds as the length of time during which an event is occurring. So in physics, when you start measuring, when you start carrying out a measurement, okay, you want to find out, let's say for example, as we're going to say, for 10 seconds, you want to find out what was the speed of this car, or what was the speed of this object at the start of the 10 seconds. Then also you want to find out what was the speed or the velocity of this object or car at the end of the 10 seconds. So the speed at the start of the 10 seconds, that is an example of instantaneous speed or velocity. The speed at the end of the 10 seconds, that is also an example of instantaneous speed or velocity. That is the kind of instantaneous speed or velocity we are interested in. We are rarely interested in what is the speed after 1 second, what is the speed after 2 seconds, what is the speed after 3 seconds, what is the speed after 4 seconds, what is the speed after 5 seconds, what is the speed after 6 seconds. We are rarely interested in that kind of keeping information like that. Okay, so the speed of an object at the beginning, when you start measuring, when you switch on your stopwatch, that is an example of instantaneous velocity, and that is what we call initial speed or initial velocity. That is interesting to us. Okay, the speed or the velocity of an object at the end of the 10 seconds, that is what we call the final speed or the final velocity. That is an example of the kind of instantaneous speed we are interested in. So in physics, in this course, we are interested in two types, in two values of instantaneous speed. We are interested in the initial velocity. We are also interested in the final velocity. That is the final velocity after a certain amount, after a certain period of time of measuring things. Is that clear?
Yes, sir.
Yes. The next kind of speed or velocity we are interested in is something called average velocity. Okay? Something called average velocity. Now, average velocity or average speed basically does not tell you what the speed was after 1 second, what the speed was after 10 seconds, because that's not how we work out average velocity. Average velocity, on the other hand, gives you a general idea of how fast an object was moving. Because for you to get average speed, what you do is that you divide the total distance covered by an object which is in motion divided by the total time. That's all. How much distance was covered divided by how much time was taken. It does not matter whether the driver stopped to go and buy Hungry Lion somewhere for 10 minutes. We are not interested in what happened. Whether you stopped for how long, we are not interested. The only interest we have is how much distance did you cover, how much time did you take. Then you divide the total distance divided by the time taken. That is average velocity. So average velocity hides a lot of information about your what actually happened. Average velocity does not tell you what actually happened. Did you hit a pothole? Did you go over a hump? What was the speed when you're going over your hump? That information is lost when you're talking about average velocity. The same thing applies with average speed. The same thing applies with average velocity. Average velocity also, you're only talking about what was the total displacement covered divided by how much time it took you to cover this total displacement. Okay? We don't care whether there was a river, you had to swim through a river or something like that. We don't care. All we know is that the displacement, which is a straight line distance, and how much time it took you to do that, cover that thing like that. So this is another way of telling us what happened. Using values of average velocity, you can come up with a conclusion. You can compare 2 or 3 objects and find out which one was moving faster than the other one based on the value of average velocity. However, you cannot do the same using values of instantaneous velocity. During this journey, which object moved faster? You do that by looking at what the average velocity was, how much distance was covered, divided by how much time it took to cover this particular distance. Are we clear? Are we clear on what the distinction is between? Debbie, your microphone, please. There's also Gabriel. Can you switch off your microphones if you're not asking questions? Debbie, Jafari, Phoenix, that microphone, we need it off. Okay. Next, here we have an example of basically what we have been talking about. So example 1, an athlete takes 10 seconds to run a distance of 100 meters. Calculate the average speed of the athlete during these 10 seconds. So the distance covered is 100 meters. Why is it distance? It's because we know the length which was covered. It's 100. However, we do not know the direction in which this particular distance was covered. That's why we're talking about distance. So we do not have information about the direction in which this athlete was actually running. But all we know is that they covered a distance of 100 meters and they did that in 10 seconds. So we can actually try to work out a value of average speed so that we can have an idea of how fast this person was running. So in order to work out the average speed, so the average speed is going to be equals to the total distance covered divided by the time taken. In this case, the total distance is 100 meters divided by the time taken, which is 10 seconds, and that's going to give you an average velocity value of 10 meters per second squared. So average velocity is v bar, 10 meters per second squared. Now, I want to stop a bit. Oh, there's something I skipped. Another way, before I proceed with the example here, another way of working out the average velocity. You can work out the average velocity based on what the initial velocity is, the value of the initial velocity, and the final velocity as follows. So you can work out the average velocity as equals to half the initial velocity, which is the velocity of the object when you start measuring the time, then plus the final velocity, which is the velocity of the object when you finish measuring the time. So you can work out the average velocity like this. So average velocity v bar is also equals to half the u plus v. That also gives you the average velocity. So instead of working out what's this? You can do two things. Either you use the total displacement. This is the average velocity. The total displacement. This is average velocity is not average speed. We're talking about average velocity here. So instead of using total displacement, you could use your initial velocity, then you can use the final velocity, add them, then you divide them by half, you still get your average velocity. So let's get back to our average speed. So this here is average speed. So we have an average speed of 10 meters per second. Now, you might be misled to believe that this 10 meters per second means that this guy was running or was covering 10 meters every second. Now, any one of you who has run or who has been involved in a race where you cover the 100 meters race, you will know that it's not possible for anyone to cover 10 meters every second, because the way you run is that you start off slowly a bit, so you cover less distance as you start, then as time goes you cover more distance, then as you approach the 100-meter mark you start to slow down. So it's not possible that this particular person or individual covered 10 meters every second. Are we clear?
Yes.
Yeah.
Yes.
In reality, the athlete does not actually cover 10 meters every second because that's not what happens. However, instead of you being troubled by what was the velocity of this athlete after at 0 seconds, what was the velocity after 1 second, what was the velocity after 2 seconds, what was the velocity after 3 seconds, what was the velocity after 4 seconds, what is the velocity after 5 seconds, what was his velocity after 6 seconds, what was his velocity after 7 seconds, what was his velocity after 10 seconds. That is a lot of values of instantaneous velocity. What you are actually given with average velocity is only one value. One value which gives you a general idea of how fast this person could have been. So average velocity does not reflect reality, but it gives you a general picture or an idea of how fast someone was running. Using values of average velocity, if another person was covering 8 meters per second, you can compare the 10 meters per second and the 8 meters per second average velocity, average speed, to find out who was running faster. So clearly, the one who was covering 10 meters per second was running faster than the one who was covering 8 meters per second average velocity. So you can use average velocity to compare values. Are we clear? So average velocity does not reflect what happened, but it gives you a general picture of how fast someone could have been running. The next physical quantity we're going to look at is something called acceleration. Like I've said, acceleration refers to how fast the velocity or the speed of an object is changing. So if the velocity is changing very slowly, then by our definition, the acceleration is low. If the speed of the velocity is changing very fast, then the acceleration is fast. And how do we define acceleration? The kind of acceleration you can have two values of acceleration, two types. There's something called instantaneous acceleration, which is the acceleration of a body in motion at a particular or at a specific point in time. But the kind of acceleration we are interested in is something called average acceleration, because remember, our interest is something called uniform accelerated motion. So the acceleration of an object at a specific point in time, that is what is called the instantaneous acceleration. We are not interested in that. Okay? Our interest is in something called average acceleration. So with average acceleration, how we work out average acceleration is you work out the change in the velocity or the speed of the object, then you divide that change in speed or velocity of an object divided by how much time it has taken. Whenever you're talking about change in a particular physical quantity, there must be an initial value of that physical quantity, there must be a final value of that physical quantity. That's what change means. Otherwise, if the initial value when you start measuring the time is the same as the final value after you've finished measuring the time, then there is no change. So in the case where the velocity or the velocity or the speed remains the same even after being measured, then in that case the change in the velocity or the speed is going to be equal to 0. So there is no acceleration or average acceleration. So average acceleration only occurs when the speed or the velocity of an object in motion actually changes. And how do we work out the change? The change is going to be equal to the final velocity or speed minus the initial velocity or the speed. So whatever the final, this average velocity depends only on the velocity after you've finished measuring the time and on the velocity when you started measuring the time. Anything happening in between here, we are not interested. That's why we call it average velocity, because it's based entirely only on two quantities: what the final velocity is and what the initial velocity is. So the final velocity minus the initial velocity divided by the time, that gives you your average velocity. So average velocity A the final velocity minus initial velocity divided by the time, and that's what you get. The v final velocity minus initial velocity, which is v minus u, this gives you the change in velocity, which is still a velocity measured in meters per second divided by the time, which is also measured in seconds, so you end up with meters per second squared for acceleration. Here we have an example of a car. A car accelerates from rest to 28 meters per second in 10 seconds. Calculate the average acceleration the car experiences. So, something happens to the velocity of the car in this 10 seconds. This 10 seconds is the duration in which the time was being measured. So we measured time for a duration of 10 seconds. This is the kind of time we're interested in our course. 10 seconds, not 10 hours or something like that. We are interested in how long an event or a process is taking place, and that's the 10 seconds. So during this 10 seconds, at the beginning of the 10 seconds, the car was at rest. At the end of the 10 seconds, the car had a velocity of 28 meters per second. So since the car was at rest at the beginning when we started measuring, then the initial velocity of the car is 0 meters per second. Then at the end of the 10 seconds, the car had a velocity of 28 meters per second. That becomes our final velocity. And the time it took for the velocity to change from 0 meters per second to 28 meters per second was 10 seconds. So we can work out an average value of acceleration. That's going to be A is going to be V minus U divided by T. So the final velocity, 28 meters per second minus initial velocity, 0 meters per second. The whole thing divided by 10 seconds. So we end up with 28 meters per second divided by 10 seconds. And that gives us an acceleration value of 2.8 meters per second squared. So that is our acceleration. That's how we present information about how fast the velocity was changing. So how do you interpret a value of 2.8 meters per second squared? Well, it means that the car increases its velocity by 2.8 meters per second every second. This is what it means. If the acceleration is 2.8 meters second squared, then that means that the velocity of the car increases by 2.8 meters per second every second. This is what acceleration means. So, if this is acceleration 2.8 meters per second every second, if you look at this table, at t equals to 0, the car was at rest. And the velocity of the car at rest, which is 0 meters per second. After 1 second, if the velocity increased by 2.8 meters per second, then the car is going to have a velocity of 2.8 meters per second. And then after 2 seconds, this 2.8 meters per second velocity will increase by another 2.8 meters per second. So you're going to end up with 5.6 meters per second. Then after 3 seconds, the 5.6 meters per second will increase by 2.8 meters per second. Then you're going to end up with 8.4 meters per second. Then after 4 seconds, the 8.4 meters per second will increase by another 2.8 meters per second, and you're going to end up with 11.2 meters per second. Then after 5 seconds, the 11.2 meters per second will increase by another 2.8 meters per second, then you end up with 14 meters per second. Then after 6 seconds, the 14 meters per second will increase by another 2.8 meters per second, then you end up with 16.8 meters per second. Then after 7 seconds, the 7.8 meters per second will increase by another 2.8 meters per second, then you end up with 19.6 meters per second. Then after 8 seconds, the 19.6 meters per second will increase by another 2.8 meters per second, then you end up with 22.4 meters per second. And then after 9 seconds, this 22.4 meters per second will increase by another 2.8 meters per second, and you're going to end up with 25.2 meters per second. Then after 10 seconds, this 25.2 meters per second will increase by another 2.8 meters per second, and you're going to end up with 28 meters per second. Is this what really happened? I don't know, because I did not see this car, and I did not see this car And during these 10 seconds, I did not have a speed trap like the police do to see exactly whether in these 10 seconds, this is how the car was moving. Are we clear? I didn't have a speed.
sir.
Yes, I didn't have a speed trap, and haven't seen this car. But I am working based on information to say this car was at rest. Then after 10 seconds, it ended up at 28 meters per second. So I am predicting what I think could have happened. Was that what happened? Maybe not. But this is the closest you can come to predicting what happened if you did not have a speed trap and if you did not see this car. Yes.
In the example, acceleration was 2.8 meters per second squared.
Yes.
Then you concluded to say in this, then the change in velocity was 2.8 meters per second.
Yes.
Now, if you look at the figures, did you just multiply it by a second for us to have 2.8 meters per second?
What?
I'm saying that according to the calculations, acceleration is equal to 2.8 meters per second.
Yes.
Then you said in this case, the speed or velocity of the car increases by 2.8 meters per second every second.
Yes.
So for us to have this 2.8 meters per second, how did we come to this point if we are not given how to come with this one from the acceleration that we obtained in the example?
We are using the acceleration we obtained in the example
Yes.
to predict what we think would have happened.
Okay.
Okay? With this acceleration you're working out in the example, this is what is called average velocity, average acceleration. You could find out what the instantaneous acceleration is if you actually had a speed trap, because the speed trap would give you what the velocity was after 1 second, after 2 seconds, after 3 seconds, after 4 seconds, after 5 seconds, 6, 7, 8. It would give you exactly what the velocity was. So you could use that to find what the acceleration was at that particular point. Okay? But we do not have access to a speed trap. So what we are doing instead is we are making a prediction based on what we know was the initial velocity and the final velocity and how much time it took. So the only thing you can work out like that, presented with those three pieces of information, is the average acceleration. If there is average acceleration, then there must be instantaneous acceleration. But based on the average acceleration, we make a prediction to say we think after 1 second, the velocity was 2.8. After 2 seconds, the velocity was 5.6. After 3 seconds, the velocity was 8.5. After 4 seconds, the velocity was 1.2. After 5 seconds, the velocity was this, like that. Okay? This average acceleration is similar to average velocity. It is giving us an idea of trying to predict how we think this particular object moved. We don't even know whether it was moving on a tarmac, whether it was moving in a gravel road. All that information is not there. Are we clear? So reality actually might be very different from what we have here. But since you're doing physics and you're a scientist, even without being given information of exactly how what happened, we still require you to make a prediction. Is that clear?
I have a question. Yes, sir.
We are in the business of predicting what happened. Yes, there's another question?
I have a question, sir.
Yes.
So, is it important for us to know how to find instantaneous velocity? Do questions like that come?
No.
Since we have a formula.
You don't have a speed trap. The only way you can know how to find instantaneous velocity is if you go to the police and we train you to be a traffic police officer. That's how you're going to know how to find instantaneous velocity. Usually what we do, there's an experiment we do where you're using a trolley car. We will tell you how to do it, okay? But usually, no. You can live your life only just by knowing how to work out the average velocity, average acceleration.
Okay, thank you.
Yes. Any other question? Before we move forward? Okay. Now, we have what we think happened in this table. So we get this information in this table, then we can plot a graph. In the graph we're going to plot, we're going to put on the y-axis, we're going to put the velocity in meters per second, and on the x-axis, we're going to put the time in seconds. When you do that, what you end up is something which looks like this. So you've got your velocity on your y-axis, then you've got your time on the x-axis like this. So you have these points. These points are our prediction of what we think happened. As you can see, these points lie on a straight line. And the only reason why these points lie on a straight line is because we assumed that the velocity is going to increase after every second by 2.8 meters per second. So between each of these points, the difference in velocity is 2.8 meters per second, 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 2.8 meters like that. That's the difference between the points. When the acceleration is the same, then you end up with points which lie on a straight line. This is the kind of motion we're interested in. And this is what, on a paper, on a graph, uniform accelerated motion looks like. It looks like straight lines. So you draw straight lines on a velocity time graph, only on a velocity time graph. Okay. Now, with this velocity time graph, there are two things you could do. The first one is you could work out the slope of this line. When you work out the slope of this line, what you expect to get is the acceleration, or something which looks like acceleration. The next thing is what you're interested in is the area under this graph. When you work out the area under this graph, what you expect to get is the distance covered by the object. So let's start with the acceleration. So in our case, the slope or the acceleration, we're going to pick points V8, point number 8. After 8 seconds, we're going to pick this point. Then we also pick the point after 3 seconds, this one here. We know the exact values of the velocity after 8 seconds. Our predicted values, not exact. We know our predicted values of velocity after 8 seconds. We also know our predicted values of velocity after 3 seconds from the table here. From this table. After 3 seconds, the velocity is 8.4 meters per second. After 8 seconds, the velocity is 22.4 meters per second. So we can work out the slope. The slope is going to be equal to the change in velocity divided by the change in time. So the change in velocity, we use these 2 points. So it's going to be V8 minus V3, then T8 minus T3. When you do that, end up with 22.4 meters per second minus 8.4 meters per second divided by 8 seconds minus 3 seconds. So you're going to end up with 14 meters per second on top divided by 5 seconds. When you do this, you end up with 2.8 meters per second squared. This is the slope. The slope has got units of acceleration. This is the slope of a velocity time graph. That is why we like this graph, because the slope of a velocity time graph, when you work out the slope, it gives us a value of acceleration. So apart from telling us what the velocity is, these are instantaneous velocities. These dots are trying to represent instantaneous velocities. So apart from telling us what the instantaneous velocities is at each and every point, when you work out the slope of this graph, what you end up with is acceleration. So it tells you how fast the velocity is actually changing. That's the first thing. The next thing of interest with the velocity time graph is the area under this graph. So if you start from here, you go up like that, up to that point, then you come down this way, you can see what you have is a triangle. Okay, the base of the triangle is measured in time, so that's 10 seconds. So the base of the triangle is the duration through which this particular thing was happening. Then the height of the triangle from there up to there, so you start from 0 up to 28, that is the change in the velocity. So the base of the triangle is the time taken to make the change in velocity. Then the height of the triangle is actually the change in the velocity. So when you get this information, the base 10 seconds, then the height of the triangle 28 seconds, then you work out the area of the triangle. The area of the triangle is equals to half times base times height. You do that, that's going to be half times 10 seconds times 28 meters per second. When you work this out, you end up with something which looks like this: 140 meters. It has got units of meters. So this makes us conclude that the area under a velocity time graph is equals to the distance or the velocity, the displacement which has been covered by the object in this 10 seconds.
Sir.
Yes.
Sir, sorry, I have a question again.
Yes.
When calculating the slope of the graph, does it matter what points we use?
Usually
Are
the
we
rule
going to get the
is
same answer?
when you're calculating the slope of any graph, you need to choose fairly separated points. Do not choose points which are very close to each other. The points should be fairly separated. That is a rule.
Oh, okay.
So any fairly separated points should be able to work.
Okay, thank you.
Any other question? Okay. So that's about the total distance under the graph. But you can also do something. You can use this same formula, the area is equals to half times base times height, to work out what the area, what distance has been moved after 1 second. So you've got a small triangle here. What's the distance which has been moved after 2 seconds? You've got a small triangle there. What is the distance which has been moved after 3 seconds? You've got a small triangle there. What is the distance which has been moved after 4 seconds? You've got a small triangle there. What is the distance moved after 5 seconds? You've got a small triangle there. What is the distance moved after 6 seconds? You can work out that triangle. What is the distance moved after 7 seconds? You work out that triangle. What is the distance moved after 8 seconds? You work out that triangle. What is the distance or displacement after 9 seconds? You work out that triangle. What is the distance or displacement after 10 seconds? You work out that triangle. When you do that, then you come up with a table like this. Say after 1 second, the distance is 0. After 0 seconds, 0, 0. After 1 second, the object moves, the car moves 1.4 meters. After 2 seconds, it moves 5.6 meters. After 3 seconds, it moves 12.6 meters. After 4 seconds, 22.4. After 5 seconds, 35 meters. After 6 seconds, 50.4 meters. After 7 seconds, 68.5 meters. After 8 seconds, 89.6 meters. After 9 seconds, 103. After that, then after 10 seconds, 140. You do this graph. You draw this graph. This graph is a displacement type graph. It's telling you, showing you how the distance or the displacement increases as time passes. As you can see, the spacing between the displacement values in terms of the points in terms of displacement widens further and further between this point and that point. The points are further. Yes.
How are we getting the values again? For the displacement.
You're using this. Half times base times height. So you start with this point, the first point and the second point. You work out a triangle. You see that? From the first point to the second point, then you come down like that. That's a small triangle. So you work out the area of this small triangle. Then this first point and this point here, you work out the area of this triangle. That's after 2 seconds. Then this first point and the third point there, that point there, after 3 seconds, you work out the area of that triangle. So you keep on doing that for each of these points. And when you work out the areas, you will find these numbers. Is that clear for everyone?
Okay, thank you.
Yes. Yes, that's how you work out the distance covered under thing. So you can have a picture of how much distance was covered after each and every second. Now you will notice that the distance covered after every second increases as the time increases, because the reason is because the object is moving faster and faster. An object which is moving faster covers more distance. Okay. The other thing you could do is you could ask yourself how much distance was covered between 4 seconds and 8 seconds. So 4 seconds is this point here, 8 seconds is that point there. So you could work out the area between these times, from there to here. You come back like this, and you see that this is a trapezium. So when you work out the area of this trapezium, that is going to give you how much distance was covered between 4 seconds and 8 seconds. So you can do a lot with a velocity time graph. You can find the acceleration, it shows you what the instantaneous velocity is, you find the distances and all sorts of things. The last but thing I want to point out is when the acceleration of an object is positive, like in this case, it means that the velocity values are going to increase like that. Okay. On the other hand, when the acceleration is negative, here this is acceleration, it's constant, so this is what we're interested in. We're interested in a situation where we think the acceleration is constant throughout. On the other hand, when the acceleration is negative, like this, it means that the velocity of that particular object is going to reduce. So an object which is undergoing negative acceleration is basically an object which is slowing down. An object which is undergoing positive acceleration, we mean that the object is moving faster and faster. Are we clear?
Yes.
Okay, so we come to the end here. You can entertain yourselves with the other graphs, try to reproduce these things and see. So I want you to use this graph, and try to see if you can produce this. Okay, so you work out the area under here. So you'll be using a trapezium now from here. You work out the area like that, you work out the area under there, like that. Now you'll be using a trapezium coming down this way, so that you can try to produce this graph. And of course the acceleration is the same, negative, because they're slowing down. Okay, I hope there are no questions. I'm still at home, so I need to rush to campus. I have got an engagement at 10 hours. So I hope you guys don't have any questions. During the course of the day, the video is going to be uploaded to YouTube and also to Moodle so that you can watch. Apologies for Monday. I couldn't make it on Monday because there's a training we are doing and we were struggling, so I had to be there, and eventually we succeeded, but that was done at the expense of not seeing you guys.